Okay, this video is for AP Calculus, and we are now in the unit on applications of derivatives. So in the last unit, we talked about ways to compute derivatives. Now we're going to focus on where can they be used. And the first one is not like a direct, like a word problem application. It's just a way to take certain kinds of limits. So this one is entitled Indeterminate Forms and L'Hopital's Rule. And it's named after a French mathematician. Sometimes L'Hopital is spelled with an S, but it's pronounced L'Hopital. Okay, so whenever we're evaluating a limit, let me just take a really basic limit here. Let's say we're taking the limit as x approaches 3 of 2x squared plus 1. Right? There's a lot of ways we can find a limit, right? We said originally you could make a table and show what's happening as x approaches 3 from the left and x approaches 3 from the right. And if they're both approaching the same y value, then that means the limit is that y value that's being approached, even if you can't literally plug 3 in. We also said that the fastest way to be able to evaluate a limit is to just try to plug that into the rule. If you can, and you get 2 times 3 squared plus 1, that's 9 times 2 is 18, plus 1 is 19, then that means that if you were to graph this function, which is some kind of a parabola, then as you're approaching 3, this number that is being approached above and below is going to be 19 on both sides. But as long as the function's well behaved enough, you can just plug the number in. But there's also other structures. So let's say you have the limit as x approaches 3 of x squared minus 9 over x minus 3, right? And if you tried to plug that in, then you would get a divide by 2 situation. But this one's fixable because you can factor on the top here and get x minus 3 times x plus 3 over x minus 3, and because you can factor and cancel those things, that's equivalent to x plus 3, which means it's just x plus 3, which is 6, or sorry, 3 plus 3, which is 6, which means that although this function looks like, if you were to graph it, it would look like a line, there's actually a hole at x is 3, but the number that's being approached is 6, right? If you can factor and cancel and give it another algebraic expression that's similar to the original algebraic expression, and then you can successfully plug in, then that means that even though there's a hole right there potentially in the original structure, right, the y value that's being approached is 6 in this case. Right, so the goal is to try to get something where you can plug in the target x and evaluate. And when you do that, you're going to get different results, right? You might just get a number, which is perfect, right? Like 6, like we did before. You might get a number over a number, like 2 over 7. That's fine. That's a number too. You might get 0 over a number, and 0 over any number other than 0 is just 0. Right? You take a pizza and you divide it into 4 pieces of pie, and you take none of them, you get no pizza. Right? You can also get any number, but over an infinity. Like if you have 4 over infinity, or something that's approaching infinity, then that's getting closer and closer to 0. Although you shouldn't really write it like that, but anytime you have a number over an infinity, that's a 0. But if you have any of the following situations, then we have to investigate further. If we have a number dividing that's getting close to dividing by 4 or 0, when we are plugging in the number, we get a 0. If those zeros in the denominator along with the number, that's potentially an issue. If you ever have a 0 times an infinity, that could be an issue, right? Because we're not sure, right? What's happening here is, this part of the expression is trying to go to 0, and this part's going to infinity, and they're multiplied. This one's trying to make it a 0, that's trying to make it an infinity, and they're fighting it out for control. Right? The same thing is true here. If you have a 0 over a 0, or an infinity over an infinity, the numerator and denominator are fighting for control here, right? If the numerator wins out here with the 0, then it'll be a 0. If this goes to 0 faster than this one, then this will go to 0, right? On the other hand, which one is the larger infinity determines whether this is going off to infinity or whether it's going off to 0, or maybe some other number, right? Like let's say you're taking the limit as x approaches infinity of 3x squared over 5x squared. Right? They're both x squared, so whatever number you plug in there, they're basically the same. This number is the same, and this is actually approaching the number 3/5. Right? So this is an indeterminate form because we can't tell whether if as x goes to infinity, let's say, that that this is going off to an infinity, or it could be going off to just a number, or it could be going to zero. So we just have to investigate further, and L'Hopital's rule provides a way to do that. Okay, so before we get into that, let's talk about this case. Anytime you have a structure where when you're about to plug in a value to evaluate a limit analytically, you're about to divide by zero and there's no way to cancel and factor that out and cancel it. If you have an uncanceled denominator zero, then that means the graph definitely has a vertical asymptote at that location. So that means if the limit is one-sided, you could declare that it's either negative infinity or positive infinity. If it's two-sided, you have to just declare the limit does not exist. So let's just work these three examples to show what's going on here, right? If I have this structure right here, limit as x approaches 3 from the left, this structure here. Now this does actually factor. It factors into, this is, let's see, x plus 2 minus x plus 3, but then divided by x minus 3, that factoring doesn't help me because I can't factor and cancel anything. That means I definitely have an uncanceled 0. And then, since I'm approaching from the left, what I would do next is switch to considering what happens just to the left of 3. So I'm going to plug a number that's close to 3 in there, like 2.99 or something. And then I'm just going to keep track of the signs. Because if I have an uncanceled 0, this is either going off to positive infinity or it's going off to negative infinity. I just need to know the sign. Right? So if I plug 2.9 in here, that would be a positive term. This would be a positive term. But then in the denominator, this would be a negative term. And a positive divided by a negative means that this limit is, you can say, approaching negative infinity. Or some teachers would say you can say equal to negative infinity. Right, since that's expressed as a one-sided limit, it's legal to say that it's an infinity. It's also okay to just say it does not exist, because technically a limit has to be a number, and infinity isn't a number. Okay, if we did the same thing here, we're going to find that this does not factor and cancel. So if I plug a number just above 3, like say 3.1, then that means that I would get like 3.1 plus 2, 3.1 plus 3 over 3.1 minus 3. I'm using this structure here to evaluate. That's going to give me a positive number over a positive number, which means this is approaching positive infinity. Or you can say it does not exist. Right? But if it doesn't specify a direction, as soon as I recognize I have an uncanceled 0 in the denominator, then I'm just going to say does not exist, because you're not allowed to say that infinities are equal to each other on the left and the right. So two-sided limits are always called does not exist. Okay, so uncanceled zeros in the denominator, and you have the vertical asymptote. Okay, now this structure where you have a 0 in the denominator, but you also have a 0 in the numerator at the same time, that's different. Right? That's called an indeterminate form, a specific term. And it can also be any infinity over an infinity, like positive infinity over positive infinity, or negative infinity over positive infinity, over negative infinity. And in that case, there is a theorem that says that as long as you can show that the numerator and the denominator are both zeros or both infinities, then the original limit as x approaches some number of f of x over g of x is equal to that same limit, but you replace the numerator with its derivative and the denominator with its derivative. Now, not quotient rule, but individually replaced. The result of limit is also, if you then plug in, you'll get hopefully a number. But if you get another indeterminate form, you can apply L'Hopital's rule over and over again until you finally get a number that is not in an indeterminate form. Now, on the AP exam, College Board has a very specific way they want to see work shown at least the first time that you evaluate in a problem, a L'Hopital's problem. So I'll show you that here in the next one. Let's say we have this limit right here. We're taking the limit as x approaches 0 of e to the 2x minus 1 over x. Okay. Well, I can see that if I plug this in, I have a divide by 0 in the denominator. So I'm going to see if that's true in the numerator as well. So what we should do is do separate limits for the numerator and the denominator. So to evaluate this, I'm going to say the limit as x approaches 0 of the numerator, which is e to the 2x minus 1, I can evaluate by plugging in a 0 here. That gives me e to the 0, which is a 1. 1 minus 1 is 0. So I'm going to show in a line that the numerator's limit is equal to 0. And then separately, I'm going to show that the denominator's limit is 0. That's also equal to 0. Then I'm going to say we have the 0 over 0 is an indeterminate form. Indeterminate form. So we can use L'Hopital's rule. So we're invoking a rule, and now I can say that this limit, the original limit, x approaches 0 of e to the 2x minus 1 over x is equal to that same limit as x approaches 0, but I get to replace the numerator with its derivative. So that is the copy times the derivative of the inside, which is 2. So 2 times e to the 2x. The derivative of that constant is 0, and the derivative of x is 1. Now I can plug this in without having to evaluate numerator and denominator separately. It's simply 2 times e to the 2 times 0. E to the 0 is 1, so this is 2. So this limit is in fact equal to the number 2. Okay, so that is how we use L'Hopital's rule, and that's the official way to show work. Let's do another example. I'll switch colors here. So let's say I've got this. I've got something where I'm plugging a large number in here, and I'm getting an infinity, and e to the negative infinity, that's actually going to be an infinity as well. So I believe this is the form infinity over infinity, but to show that, I'm going to show the limit in the numerator as x approaches negative infinity of x squared is equal to, now I'm not going to plug in an infinity, right? You don't want to really do arithmetic with infinities because they're not numbers. But if I took a large negative number and I squared it, I'm just going to get a large negative number. So we're just going to say that that's approaching infinity. And some teachers like the arrows, some teachers will say equals. The arrow's a little safer. Limit in the denominator, limit as x approaches infinity of e to the negative x that's the same as plugging a negative in. So just thinking about this for a second, if you think about an e to the x curve, e to the negative x is an exponential decay curve like this. And that means as we go off to negative infinity here, this is going off to positive infinity. So I'm just going to state that that is positive infinity. Therefore, we have the indeterminate form, infinity over infinity. So we can use L'Hopital's rule. Okay, so that's going to say that the limit as x approaches negative infinity of the original limit, x squared over e to the negative x, is equal to the limit as x approaches negative infinity of, replace this with its derivative, which is 2x, and the denominator, e to the negative x, gets replaced with the copy times the derivative of the inside, so that's negative e to the negative x. And now that, if we plug in here, gives me a negative infinity over a negative infinity. Now, should we do this over again? Should we show the limit on the numerator and the numerator again? On their own rubrics for College Board, they will, once they've shown this one time, they'll just say this approaches negative infinity over a negative infinity, which is an indeterminate form. So they kind of use a shorthand on the second time period. And then we can just say L'Hopital's. And we can say that this is now equal to this limit as x approaches negative infinity of the derivative of 2x, which is a 2, and then the derivative, which is a copy again, times a negative, so it switches back to a positive with negative x. Now we have, this is going off to an infinity, and this is 2. So 2 over infinity, anytime you have a constant divided by something getting large, that limit we can assert is equal to 0. And so that is in fact the answer. This limit is equal to 0. Okay, let's take a look at a few more examples of this. All right, another limit, x approaches infinity. We got a polynomial on top, right? This is going to go to infinity, that's going to go to infinity. Since the first time through, I'm going to show that we're separately evaluating the limit on the numerator. That is 3x squared plus x. That is equal to an infinity, plus an infinity is infinity, so I'm going to say it goes to infinity. For the denominator, limit as x approaches infinity of parentheses around that, 4x minus 7. That's a giant number. Take away 7, it's still a giant number. It means I have the indeterminate form, infinity over infinity. So use L'Hopital's rule. So that means that the limit as x approaches infinity of 3x squared plus x over 4x minus 7 is equal to the same limit as x approaches infinity of the derivative of this. So that's going to be 6x plus 1 over 4. Now, the numerator here is going off to an infinity. I have an infinity divided by 4, which is just going to infinity. So we can state that this is going to infinity. You can say equals to infinity, or you can say does not exist, because technically if it's anything other than a finite number, it does not exist. Okay, so those three cases are the most typical kind of things we would see using derivatives to evaluate a limit using L'Hopital's rule. Now, there's some more esoteric cases that sometimes come up. Here's an example of that. So anytime you get a limit where you have things that are not in the form of a fraction, but they're a product, two things that are multiplied, you can sometimes rearrange things so that they can become L'Hopital's rule. So what I could say is maybe using the same kind of structure that they were using before, to do things separately, I can show the limit as x approaches infinity of this left factor, e to the negative x. Right? So just thinking of an exponential decay curve, as x goes to infinity, that goes off to 0. So I can assert that that limit is 0. And then on the right side, the limit as x approaches infinity of the square root of x is an infinity. Right? So this is not officially called an indeterminate form, but I'm just going to note that it's a 0 times an infinity, which means I think I can rearrange this. So to try to get it into one of the official indeterminate forms, where it has to be in the form of a fraction, either 0 over 0 or infinity over infinity, what we can do is maybe move this to the bottom side of the fraction and write this over again as a fraction. So I'm going to assert that this limit is equal to this limit, where I've got the square root of x over e to the positive x. So moving this to the other side of a fraction makes that there. Now, what I can do is use the numerator, limit as x approaches infinity of the square root of x, that's infinity. The limit as x approaches infinity of e to the x is infinity. So now I can say we have infinity over infinity, which is an indeterminate form. So we are allowed to use L'Hopital's rule. Okay, so that means that we can state that this is limit as x approaches infinity of the derivative. Now, this is equivalent to x to the 1/2 power here. So the derivative would be 1/2 x to the negative 1/2 by the power rule, and the derivative of e to the x is e to the x. Algebraically, that's the same as a fraction with a 1 on the top, and on the bottom we have this 2. We have this e to the x, and we have this x to the negative 1/2, which would move to the bottom and become a positive 1. So really it's this. And if you plug an infinity in here, e to the infinity is infinity, that's an infinity. So you have a constant over infinity. Anytime you have a constant over an infinity, that's just 0, right? 1 divided by a billion, 1 out of a billion is very close to 0. So you can assert that that's equal to 0, so this limit is equal to 0. Okay. So if you have something that's resolving to a 0 times an infinity, when they fight for control, usually you can just move 1 to the other side of the fraction to force it in fraction form, so we can get one of the official indeterminate forms, infinity over 0 over 0 to proceed. Okay, one last special case. If you're taking a limit and you have a function raised to a function, we're going to do something like logarithmic differentiation. We're going to employ a logarithm. So to solve this case, I'm going to, you're required to do that anytime you're taking a limit with a function raised to a function. I'm going to define a new letter like y equals the limit that we're trying to find. Limit as x approaches 0 from the right of sine of x raised to the x power, so that I can take the logarithm of both sides. So if I take the logarithm of both sides, and I get to do a few things. The first thing is there's a property of limits that says that if you have a limit, a function containing a limit, and you can take the limit of the resulting function. So you can swap these two things. So by theorem, this is equal to the limit as x approaches 0 from the right of the natural log of sine of x raised to the x. But because this is a log now, and we have the entire argument to the input to log being raised to the x, this x can come down on the outside. So now I can write natural log of y is equal to the limit as x approaches 0 from the right of x times natural log of sine of x. All right, then we can evaluate this. Now, as we plug a 0 in here, let's see, this one was natural log of sine, yeah, okay. So let's see what's happening. We've got a product here, so let's actually do what we did before. I'm going to change colors here. And we will investigate each of these product factors separately. So what if I take the limit as x approaches 0 from the right of x? Well, that's simply 0. What about the log? The limit as x approaches 0 from the right of natural log of sine of x. Well, sine of x, right, if you think of a unit circle, as we're getting closer to 0 from the right-hand side, that means the angle is getting closer to 0. And that means the sine is getting, the sine is the y, so this is the 0.10. So the sine is getting closer to 0 as well. So this is getting closer to 0. You could almost say this. You could say, maybe I should say it this way. The limit as x approaches 0 from the right of sine of x is approaching 0. So that is 0. But we're approaching from the higher values. In other words, the sine starts out as like 1 and then 0.9, 0.8, 0.7, 0.1, and it's getting, so we're approaching this from the, should say this, that this limit approaches 0 from the right. Right, so that means then if I take the natural log, if I take the limit as its input approaches 0 of the natural log of just x, what does the natural log function look like? It looks like this, goes to the point 1, 0, but as this x is approaching 0 from the right-hand side, the logarithm of that is approaching negative infinity. So actually this is approaching negative infinity. That means I have this case where we have a 0 times a negative infinity, which means we should be able to rearrange this to be in a form where we can use L'Hopital's rule. So the next step I'm going to do over here in the main limit is I'm going to rewrite this limit, x approaches 0 from the right. I'm going to take this natural log and leave it on the top, sine of x. And I'm going to write this x as 1 over 1 over x. I'm going to move it to the bottom of the fraction like that. Because then I can now say this, the limit as x approaches 0 from the right of the numerator, we just showed with this work, is approaching negative infinity, and the limit as x is approaching 0 of 1 over x is approaching positive infinity. Because we're getting closer and closer to dividing by 0, we have a positive divided by a positive. So that means we have the indeterminate form, negative infinity over infinity, which means we can use L'Hopital's rule. So by L'Hopital's rule, this is equal to the limit as x approaches 0 from the right of the derivative of this. So now what's the derivative of natural log of sine? Well, that would be 1 over the input times the derivative of the input, which is cosine. And this is equivalent to x to the negative 1 on the side. What is the derivative of x to the negative 1? Negative x to the negative 2. That would be negative 1 over x squared. Right? And that means I can do some more manipulation here. Let me get some more space. So this is equal to the limit as x approaches 0 from the right. I'm going to move this back to the top of the fraction. Well, let me write this fraction first of all. This is the fraction of cosine over sine. And then this is on the denominator, so if I move this back up here, the x squared would be on the top, and then we have a negative. So this structure is the same as that. And then we can write it one more way too. Cosine over sine is a cotangent. So I could say this is equal, actually, work here. Limit as x approaches 0 from the right. This is a negative x squared. This cosine over sine on the top, right here, could move to the bottom of the fraction and become a tangent. Let me back up for a second and make that a little clearer. I think there's too many lines here. Okay, so instead, let me do this. At this stage, I'm going to declare this cotangent of x, so that I can say this is the same as limit as x approaches 0 from the right. If I move this to the top, it becomes negative x squared. If I move cotangent to the bottom, it's 1 over that, which is tangent. Right, so now, if I imagine plugging in something here, I'm going to get the numerator derivative is 0. I'm sorry, the numerator, if I plug a 0 in, is 0. Tangent is what? So a lot going on in this problem. Okay, at the angle 0, we have 1, 0. The tangent is sine over cosine, so that tangent of 0 be 0 over 1, which is 0. So this is 0, which is another indeterminate form. And when you have a long problem like this, they want to see the separate limits for numerator and denominator once, but then you can just say, okay, this is another indeterminate form, so use L'Hopital's rule again. That means I can take the limit again as x approaches 0 from the right and replace this with the derivative, negative 2x. The derivative of tangent is secant squared. Right? But secant squared, secant is 1 over cosine, so that's actually the same as the limit as x approaches 0 from the right of negative 2x cosine squared of x. And now I can actually plug in and evaluate. If I plug a 0 in here, I have negative 2 times 0 times cosine of 0 squared. And so that whole thing is 0. A bit more room. Now, all of this on the left side is natural log of y. We'll fill those in. I want to make sure we don't forget that, because if the natural log of y is 0, that means that to get rid of this y, to solve this for y, I can say e to the left equals e to the right. And that would cancel and give me y is equal to e to the 0, which is 1. And we defined y to be our original limit. So therefore, this original limit, which was, right this way, the limit as x approaches 0 from the right of sine of x to the x is in fact equal to 1. Ooh, that is an intense problem. There is a lot going on there. So the point is, whenever you have a limit where you're evaluating a function to a function, you're required to set that equal to a variable, you usually call it y, and then introduce a log so that you can move this x down and use product rule. When you evaluate the limits, you'll typically get a 0 times an infinity, which means you can rearrange it so that you can do L'Hopital's rule. This one requires multiple applications of L'Hopital's rule. Okay, There are a lot of additional problems. Rather than make this video super long, what I'm going to do is make a second video where I go through all of these examples. So if you would like to see even more examples, go ahead and watch the second video.